Hello, hello. Yeah, welcome back to yet another devlog. It's again, I forgot the number. It's probably somewhere around 11 or 12. This hopefully is the last one that I'm going to cover Zigling. Basically, we are going to finish the all the Zigling exercises that are available in the self-hosted compiler, and then I need to review back some of the items I picked up through the way for further review and get back to them. I'm planning to also record some dedicated videos summarizing what I learned in this journey. This was definitely a nice experience for me. But let's not get ahead of myself and first finish the remaining exercises. So, number 100. We've seen that the for loop can actually, let me check. Is this the one I need to do first? Yes, it is the one. We've seen that the for loop can let us perform some action for every item in an array or a slice. More recently, we discovered that it supports ranges to iterate over number sequences. This is part of a more general capability of the for loop, looping over one or more objects where an object is an array, a slice, or a range. In fact, we did use multiple objects way back in exercise 16, where we iterated over an array and also a numeric index. It didn't always work exactly this way, so exercise had to retroactively be modified a little bit. This is it. I think in the previous exercise it was 9. Okay. 099, where there was an interesting for loop somewhere. Let me check this. Not 98, 97. I'm pretty much sure last night I saw something that took my attention. Yes, this one. So yeah, I remembered from exercise 16 or somewhere before that we had a for loop like this, and then we had an object that we wanted to iterate, and also to have the indexes we were passing on something like this, right? A range of numbers. What happened here basically then is basically I learned that there is nothing special about this syntax. You can just put two objects there for you to iterate over. Yeah, basically this syntax summarizes it quite well. List A, list B, basically two iteratable. One question for me would be what happens if the lists don't have the same size. What's really beautiful about this is that we don't have to keep track of an index or advancing a memory pointer for either of these lists. That error prone stuff is all taken care of for us by the compiler. Below we have a program that is supposed to compare two arrays. Please make it work. So we have two array of the same size, 3, and then basically this would be decnums, and then what they call dn, right? I think it's quite simple to make it work. Yes, array is meshed. You're perhaps wondering what happens if one of the two lists is longer than the other. Try it. Okay, let's do, for example, 120. And then zig run exercise 100. Oh, beautiful. It's a compilation error. Okay, interesting. By the way, congratulations for making it to exercise 100 celebration area. Please keep your celebration within the provided area. Okay. Nice joke. Number 100 solved. Let's go for 101. The for loop is not just limited to looping over one or two items. Let's try an example with a whole bunch. What do you mean by that? But first, there is one last thing we've avoided mentioning until now, the special range that leaves off the last value. That's how we tell Zig that we want to get a numeric value for every item in things starting with 0. A nice feature of these index ranges is that you can have them start with any numbers you choose. Okay. I was a little distracted. I'm seeing the stream over here. I'm not sure if it's streaming correctly. I just wanted to record me. I don't care about being streamed. Let's check the YouTube. I think there is a big delay in what's happening here, so I'm going to close it to not distract me for the time being. Or maybe even better to open YouTube, my channel. Yeah, it seems I'm receiving a good stream feed. Okay, back to the problem. Remember our RPG characters? They had the following properties which we stored in a struct: class, gold, experience. What we are going to do now is to store the same RPG character data but in a separate array for each property. It might look a little awkward, but let's bear with it. We've started writing a program to print a numbered list of characters with each of their properties, but it needs a little help. Okay, let's see what is the error first. 101. Okay, there are some question marks. We have std, we have print, we have roll in and then here are the three property arrays. We have roles, we have gold, we have experience. We would like to number our list starting with 1, not 0. How do we do that? Easy, right? And then const role name switch C wizard. Yeah, basically for each of the role names we are passing on a role name to this based on the roles. Yeah, and then we just print the role name, the index starting from 1, the amount of gold and experience. Is that it? Beautiful. By the way, Storing our character data in arrays like this isn't just a silly way to demonstrate multi-object for loops. Yeah, this was interesting that we could iterate over many objects at the same time. It's also a silly way to introduce a concept called a data-oriented design. Let's use a metaphor to build up an intuition for what this is all about. Let's say you've been tasked with grabbing 3 glass marbles, 3 spoons, and 3 feathers from a magic bag. But you can't use your hands to grab them. Instead, you must use a marble scoop, a spoon magnet, and feather tongues to grab each type of object. Now, would you rather to use the magic bag? Group the items in clusters so you have to pick up 1 marble, then 1 spoon, then 1 feather, or group the items by type so you can pick up all of the marbles at once, then all of the spoons, then all of the feathers. If this metaphor is working, hopefully, it's clear that the B option would be much more efficient. Well, it's probably comes a little surprise that storing and using data in a sequential and uniform fashion is also more efficient for modern CPUs. Decades of object-oriented practices have steered people towards grouping different data types together into mixed type objects, with the intent that these are easier on the human mind. Data-oriented design groups data-oriented design groups data by type in a way that is easier on the computer. With clever language design, maybe we can have both. In the Zig community, you may see the difference in grouping presented with the terms array of structs versus structs of arrays. To envision these two designs in action, imagine an array of RPG character structs, each containing 3 different data types, versus a single RPG character struct containing 3 arrays of 1 data type each, like those in the exercises above. For a more practical application of data-oriented design, watch the following talk. I'm going to bookmark this for later to get back to this. I think it should be quite a long video. Yeah, again, 45 minutes. I also have another one from yesterday that I need to get back to, but for now I'm going to skip to not distract myself. So 101 is also solved. Let's go to testing and take a sip of coffee. It's getting cold. Colder it is, the taste gets worse. This coffee I don't like that much, so I need to just finish it. Okay. A big advantage of Zig is the integration of its own test system. This allows the philosophy of test-driven development to be implemented perfectly. Zig even goes one step further than other languages. The tests can be included directly in the source file. This has several advantages. On the top hand, it is much clearer to have everything in one file, both the source code and the associated test code. On the other hand, it is much easier for third parties to understand what exactly a function is supposed to do if they can simply look at the test inside this source and compare both. Yeah, this is, I think, a practice also in Go language, happens a lot. Also Rust, I believe. not Python. You need a different file name. Especially if you want to understand how, for example, the standard library of Zig works, this approach is very helpful. Furthermore, it is very practical if you want to report a bug to Zig community to illustrate it with a small example, including a test. Therefore, in this exercise, we will deal with the basics of testing in Zig. Basically, tests work as follows. You pass certain parameters to a function for which you get a return. The result, this is then compared with the expected value. If both values match, the test is passed, otherwise an error message is displayed. Testing expect, value expected. Also, other comparisons are possible. Deviations or also errors can be provoked, which must lead to an appropriate behavior of the function so that the test is passed. Tests can be run via Zig build system or applied directly to individual modules using Zig tests XYZ Zig. Okay, this only runs the tests then, okay? Both can be used script driven to execute tests automatically after checking into a Git repository. Yeah, something we also make extensive use of here is at Ziglings. Yeah, this is visible. This is a simple function that builds a sum from the passed parameters, the associated test. It always starts with the keyword test, followed by a description of the tasks of the test. This is followed by the test cases in curly brackets. Yeah. And then we have a try expect. The first test checks if the sum of 41, and yeah, this is clear. And then another simple function, subtraction, testing subtraction, and a division function. We want to here receive division by 0 error. Go to top and Zig build it. Okay, in sub there is an error. Test divide, okay. Second test, try. Okay. This is how it works. Cool. I really like this syntax. It's quite simple to follow. Let's go for number 03. The functionality of the standard library is becoming increasingly important in Zig. First of all, it is helpful to take a look at how the individual functions are implemented, because this is wonderfully suitable as a template for your own functions. In addition, these standard functions are part of the basic configuration of Zig. This means that they are always available on every system. Therefore, it is worthwhile to deal with them also in Ziglings. It's a great way to learn important skills. For example, it is often necessary to process large amount of data from files, and for this sequential reading and processing, Zig provides some useful functions, which we will take a closer look at in the coming exercises. A nice example of this has been published on the Zig homepage, replacing the somewhat dusty hello world. Nothing against Hello World, but it is just it just doesn't do justice to the elegance of Zig, and that's a pity. If someone takes a short first look at the homepage and doesn't get doesn't get enchanted, and for that the present example is simply better suited, and will therefore use it as an introduction to tokenizing, because it's wonderfully suited to understand the basic principles. Let me see what they are talking about. Okay, there is a sponsorship message. Maybe we should consider that. And then the program. Yeah, there is no hello world. I didn't notice it. What are they doing here? Parse int from fmt, parse integers, allocator, ensure the list is freed at the scope exists, and then tokenize any from the input it, and then have iteration on top of it. Okay, this was interesting. So there is a next method on this iterator, tokenize iterator, and then try to parse the values, and every time it is going to split on this, oh, either a space or comma, I believe that's what it means. The expected is 123, okay, and then for expected list items, texting expect equal. Okay. In the following exercise, we will also read and process data from large files, and at the latest, then it will be clear to everyone how useful all this is. Let's start with the analysis of the example from the Zig homepage and explain the most important things. Constant steady, yeah. Here a function from the standard library is defined, yes, that I understood, and then either by comma or a space, yeah, and then in order to be able to process the input value, memory is required. An allocator is defined here for this purpose. The allocator is used to initialize an array into which the numbers are stored. Okay. This way you can never forget what is urgently needed, and the compiler doesn't grumble either. Okay. Yeah, now it gets exciting. A standard tokenizer is called. Zig has several and used to locate the positions of the respective separators. We remember a space and comma and pass them to an iterator. Yeah, that's what it meant. Then the iterator can now be processed in a loop, and the individual numbers can be transferred. Yeah. But be careful, the numbers are still only available as strings. This is where the integer parse comes into play, converting them into real integer values. Finally, the individual values are stored in the array. Yeah, there was a small difference between these two. Yeah, here how the array is initialized. Here it was like this, and then it was initializing an empty array like this. This was interesting. and compared to this one where we have array list init alley where we are passing the allocator, but this one didn't need an allocator, right? This GPA, oh wait a minute, is used down here when we are appending. But this append doesn't need a GPA. Okay, then there are two different syntax. I'm not sure. Probably this one is hopefully the latest one. And this one is just not updated or using a deprecated syntax. For the subsequent test, second static array is created, which is directly filled, and then we iterate over them and convert them. So much for an example from the homepage. Let's summarize the basic steps again. We have a set of data in sequential order, separated from each other by means of various correctors. For further processing, for example, in an array, this data must be read in, separated, and if necessary, converted into the target format. We need a buffer that is large enough to hold the data. This buffer can be created either statically at compile time if the amount of data is already known, or dynamically at runtime by using a memory allocator. The data are divided by means of tokenizer at the respective separators and stored in reserved memory. This usually also includes conversion to the target format. Now the data can be conveniently processed further in the correct format. These steps are basically always the same, whether the data is read from a file or entered by a user via the keyboard, for example, is irrelevant. Only subtleties are distinguished, and that's why Zig has different tokenizers. But more about this in later exercises. Now we also want to write a small program to tokenize some data. After all, we need some practice. Suppose we want to count the words of this little poem. Okay. Now the tokenizer, what do we want here? Basically the delimiters, and then Zig build. And probably comma. What is extra? A semicolon. Okay. Okay. Cool. 103 also solved, so 102, 103. Let's go for the next one. I'm going to restart my playlist. Take a sip. We have a nice ASCII diagram down here. Let's see what is it about. And the error looks like more sophisticated. So there are many places that things are broken. Threading. Okay, cool. Whenever there is a lot to calculate, the question arises as to how tasks can be carried out simultaneously. We have already learned about one possibility, namely a synchronous process in exercise 84 to 91. We didn't, it skipped those. However, the computing power of the processor is only distributed to the started and running tasks, which always reaches its limits when pure computing power is called up. For example, in blockchains, based on proof of work, the miners have to find nonce for certain character strings so that the first m bits in the hash of the character string and the nonce are 0. As the miner who can solve the task first receives the reward, everyone tries to complete the calculations as quickly as possible. This is where multithreading comes into play, where tasks are actually distributed across several cores of CPU or GPU, which then really means multiplication of performance. Okay. The following diagram roughly illustrates the difference between the various types of process execution. The overall time column is intended to illustrate how the time is affected if, instead of one core as in synchronous and asynchronous processing, a second core now helps to complete the work in multi-threading. In the ideal case shown, execution takes only half the time compared to the synchronous single thread, and even asynchronous processing is only slightly faster in comparison. Okay, in synchronous processing, we have a blocking task, and then task 1, and then task 2. Task 1, task 2, task 1 is how asynchronous works. And then in multi-threading, we have task 1 and task 3, for example, running together, task 2 and 4 running together. The diagram was modeled on the one in a block, in which differences between asynchronous processing and multi-threading are explained in detail. At least I know. Our exercise is essentially about clarifying the approach in Zig, and therefore we try to keep it as simple as possible. Multithreading in itself is already difficult enough. Okay. And then we have this. This is where preparatory work takes place before the parallel processing begins. These curly brackets are very important. They are necessary to enclose the area where threads are called. Without these brackets, the program would not wait for the end of the threads, and they would continue to run beyond the end of the program. I don't get it. Okay. Without these brackets, the program would not wait for the end of the threads. Okay, so it's kind of when it reaches to this, it will wait for these threads to finish to get back to this scope and then finish. Okay, this makes sense. And then now we start the first thread with the numbers as parameter. Waits for the thread to complete, then allocates any resources created on a spawn, deallocates, handle join. This is why this is necessary. So we are creating multiple threads and then deferring them to wait for them to exit. So I'm wondering if it's necessary to have it here, because then the defer should also work with this scope. Third thread, after the threads have been started, they run in parallel, and we can still do some work in between. Some weird stuff happening in between. Okay. After we left the closed area, we wait until the threads have run. If this has not yet been the case, so meaning this would be also be printed before this. This function is started with every thread that we set up. In our example, we pass the number of the thread as a parameter. And then the thread will sleep number multiplied by 200 nanosecond per millisecond. This timer simulates the work of the thread. Work time 3 multiplied by whatever, then as the thread asleep. Okay, and then print. This is the easiest way to run threads in parallel. In general, however, more management effort is required. For example, by setting up a pool and allowing the threads to communicate with each other using semaphores. Yeah, this is something. I think in Go there is a similar thing to use, right? Something called, is it called channels? I think so. But that's a topic for another exercise. Okay. Then what is the error here? What's happening? Unused local constant in line 4. Okay, and then handle 3. And then usize cannot represent integer value -4. Which line is calling this? We have a usize. What happened? Usize. This is the only. Okay. So then, oh yeah. This is the nasty one. So yeah, Zig is cool is out of the context, but this is running in between somewhere. And then it starts working. Yeah, these threads are running. There is no. Okay. Syntax is understandable. I like it. And then 104 also solved. Let's go 105. Okay, this is a long tag. And the thing is, I started this stream at 11 p.m. I feel I'm sleepy, but I want to push through it. I had my coffee, but I'm still sleepy. So Let's push through. Now that we are familiar with the principle of multithreading, let's boldly venture into a practical example for mathematics. We will determine the circle number pi with sufficient accuracy. There are different methods for this, and some of them are several hundred years old. For us, the dusty procedures are surprisingly well suited to our exercise because the mathematicians of the time didn't have fancy computers with which we can calculate something like this in seconds today. Whereby, of course, it depends on the accuracy, how many digits after the decimal point we are interested in. But these old procedures can still be tackled with paper and pencil, which is why they are easier for us to understand, at least for me. Probably for me too. I'm not a mathematician. So let's take a mental leap back a few years. Around 1672, if you want to know and read about it in detail, you can do so on Wikipedia, for example. Various mathematicians once again discovered the method of approaching the circle number pi. There were the Scottish mathematician Gregory and the German mathematician Leibniz, and even a few hundred years earlier, the Indian mathematician Matava. All of them independently developed the same formula, which was published by Leibniz in 1682 in the journal Acta Eruditum. This is why this method has become known as Leibniz series, although the other names are also often used today. We will not go into the formula and its derivation in details, but we'll deal with the series straight away. Minus 4 over 1 minus 4 over 3 plus, okay. As you clearly see, the series starts with a whole number 4 and approaches the circle number by subtraction and adding a smaller and a smaller parts of 4. Pretty much everyone has learned pi 3.14 at school, but very few people remember other digits, and this is rarely necessary in practice. I'm hallucinating here, because either you don't need the precision or you use a calculator in which the number is stored as a very precise constant. But at some point, this constant was calculated, and we are doing the same now. The question at this point is, how many partial values do we have to calculate for which accuracy? The answer is chewing. To get 8 digits after the decimal point, we need 1 billion partial values. And for each additional digit, we have to add a 0. Okay, this multiplied by 10 every time. Even fast computers, and I mean really fast computers, get a bit warmer on the CPU when it comes to really many digits. But the 8 digits are enough for us for now, because we want to understand the principle and nothing more, right? As we have already discovered, the Leibniz series is a series with a fixed distance of 2 between the individual partial values. This makes it easy to apply a simple loop to it, because if we start with n equal 1, which is not necessarily useful now, we always have to add 2 in each round. But wait, the partial values are alternatively added and subtracted. This could also be achieved with one loop, but not very elegantly. It also makes sense to split this between two CPUs. And one calculates the positive values and the other the negative values. And so we can simply start two threads and add everything up. At the end, we are done. We just have to remember that if only the positive or negative values are calculated, the distance are twice as large. So that the whole thing has a really learning effect. The first thread call is specified and you have to make the second. But don't worry, it will work out. Yeah, I didn't get a word of this. Let's see the code. Count 1 billion pi plus pi minus. First thread to calculate the numbers. Thread is found. No config. Function is thread pi. Pi plus. What is 5? And then no, and then count is 1 billion. Okay, handle join. What is happening here? While n, okay, this is end, this is beginning. So this was the beginning. And then 4 plus pi plus minus pi minus. Okay, and then here we are doing pi because this was a pointer. Okay, we are dereferencing it to just update this value and then add it with 4 divided by float number from int. Make sure this is a floating point number and we are using F64 to get enough space for that division. The only question for me is why we are starting from 5. We have already discovered Leibniz series is a series with fixed distance of 2. I just don't know. I'm not sure if I want to care at the moment. But here to handle 2, we are basically doing the same thing. Thread spawn and then no config thread pi no thread pi and then remove this and here has in the config pi minus and then 5 and down this and defer handle 2 that join. What is the error? Undeclared? What do you mean by that? Oh, I have a typo. Okay. It didn't work out because they are so what's happening here is that they are taking the same set of numbers. Okay, maybe it's I need to start with one number less. Is that better? No, that's too much. Okay, this +4 was helping to alternate between numbers. When I was passing the exact 5 here, which was used for plus, it was ending up with the same numbers. Then that's why they were exactly similar, and we got a 0 over here, right? When I put it as 1, it turned out the value over here would be a -4. Then we got a 0. Then I reducing it to, I just guessed out my work way through it. I'm still not sure how exactly it works, but I think that's the right logic behind it. And okay, if you wish, you can increase the number of loop passes, which improves the number of digits. We got, okay, 8 characters after the, yeah, so that's fine for now, but be careful. In order for parallel processing to really show its strengths, the compiler must be given the natural release fast flag when it is created. Otherwise, the debug functions slow down the speed to such an extent that seconds become minutes during execution. And you should remove the formatting restrictions in print, otherwise you will not be able to see the additional digits. Yeah, this is the restriction, but that's fine for now. 106 files, sip of water. That's all 106. Until now, we've only been printing our output in the console, which is good enough for fighting aliens and hermit bookkeeping. However, many other tasks require some interaction with the file system, which is the underlying structure for organizing files on your computer. The file system provides a hierarchical structure for storing files by organizing them into directories, which hold files and other directories, thus creating a tree structure that can be navigated. Fortunately, the Zig standard library provides a simple API for interacting with the file system. See the detailed documentation. Okay, in this exercise, we'll try to create a new directory, open a file. In the directory, write to the file. And then we have the current working directory out of S, which is part of SD. Then we'll try to make a new directory output to store our files in. twd make their output cache the error switch. There is a chance you might want to run this program more than once, and tasks might already have been created, so we'll have to handle this error by doing nothing. We want to catch and do nothing. Error has already exists. Then we'll try to open our freshly created directory. Wait a minute, opening a directory might fail. What should we do here? Try. And then close it. We try to open the Zigling txt and propagate any error up. Yeah, it is good habit to close a file after you are done with it, so the other programs can read it and prevent data corruption. But here we are not yet done writing the file. If only there were a keyword allowed you to defer code execution. Yeah. You're not allowed to move these two lines above the file closing line. Yeah. Beautiful. To check if you actually write the file, you can either open the file in your text editor or cat output Zigling. Yeah, it's zig time. More on creating files. Notice in create file we passed this anonymous struct to the function call. This is a struct create flag with default fields, read false, truncate true, exclusive. Question: what should you do if you want to also read the file after opening? Set read to true inside this method. Go to documentation. Can you find the function for opening the file? What kind? Okay. I think inside fs now we have a file. And then we have chmod clause. Close, not clause. Lock, yeah, everything. Read, yeah. Yeah, easy. 107. Prerequisites that's created, or we create a file. Now there is no point in writing to a file if we don't read from it. Am I right? Let's write a program to read the content of the file that we just created. I'm assuming that you've created the appropriate files for this work. All right, but let leaning close. Here's the plan. First, we open the project root output directory. Secondly, we open the file zigling.txt. In that directory, then we initialize an array of characters with all letters A and print it. After that, we'll read the content of the file into the array. Finally, we print out the content we just read. Get the current directory. Try to open output directory. assuming you did, yeah, let's create it. Try to open the file out with dir, yeah, close it. Initialize an array of u8 content. We need to pick the size of the array. 64 seems like a good number. Fix the initialization below. This should print out, yeah. Okay, seems like a threat of violence is not the answer in this case. Can you go here and find a way to read the content? The file is open. Read and pass it to the content, which is a buffer, but we need to try it as well. What? Too screamy? I know you're excited for Zigling time, but tone it down a bit. Can you print only what we read from the file? Let's see what's happening. Expected type found. Did I forget this? Or this should have been like this. No. Hmm. What's happening here? I think we learned it, right? In the exercises of array to repeat. But this is not an array. This is not what it wants. What it was doing was A64. This is not what I've seen. What this means. That's not what's happening, right? Here I'm getting error. But saving. Error because you are using the wrong syntax for array repetition. I'm not sure what happened. So I came up with the correct syntax, right? And then the correct syntax is to have it open of type U8 and then put the value you want and then multiply it 64 and you get the first bit right. Correct. But when we read it, as in the extra content we want, let me rerun the ZLS. No, it was eglot to get the types. Okay. Want to go down here. Help me understand why in this program the read is prepending to the array instead of overriding the indexes in place. I think the previous answer was confused. The copilot was confused. But I'm going to take my chances to maybe see if we get a resolution with this one. The issue is overriding the array in place, but you are printing the entire 64 byte array instead of just the bytes you were reading. Bytes read. So you mean here I need to limit it to how can I limit it to 64? Oh, create a line. Oh, change this line only. Okay, okay. It is expected to change this. So 0 up until bytes read. Yeah. So yeah, only print the bytes we read. This creates a slice. So now, okay. Alternatively, to read operation is working correctly. It just it's fine. It wasn't pre-pending. I don't get it. Why was printing like 64 items? Zig run exercises 107. This to me looks like more than 64 characters. Am I wrong? This piece itself should be, let's do Python. Len. Okay. It's just the length of my character. This. Okay. What I need to do? Go to 108. 107 also solved. Okay. Okay, I think I'm going to give up for now. I solved up until 107. There are 3 more exercises. I will get back to this tomorrow morning. It wouldn't feel like continuing it. Thanks for watching. Yeah, let me know what do you think about these exercises. For me, it's definitely a lot of context. I feel like that I'm finding my way through the exercises, but I still need time to more practice them in real life to actually master them. It's a quite interesting journey. Yeah, thanks for watching. See you in the next one.